Welcome back to Cypress Academy, PSOC 6 101. In the last video, I showed you how to use the PSOC 6 I2C master to interface with the Bosch BMI 160 accelerometer. Now we're going to add the motion sensor capability into our robotic arm remote control project. We'll start out by adding the Bosch library to the main controller project. Make a folder called Bosch and add the existing items to it. We'll change the build settings for the CM4, compiler, general, add additional include directories, then click add, then new, then add the BMI driver directory that we previously cloned from GitHub. Now we'll add the I2C component to the schematic, change it to a master, then we'll add a digital output pin called LED8. This LED will be on when you're in CapSense mode and off when you're in motion mode. Originally, when I built this thing, the CapSense and the motion sensor would kind of fight with each other. So for this implementation, when it's sitting still for a while, it'll be in CapSense mode. And when you pick it up and move it around, it'll switch to motion mode. So the next thing you need to do is assign the pins. P60 and P61 are the I2C pins. Next, run the generate application. To start the firmware, I'm going to create motion-task.h. So right-click, add, new item, then header file, then motion-task.h. First, I'll add the Pragma once. When I originally built this application, I had the CapSense task and the motion task running at the same time and independently of each other. I thought that this would be great, but they fought with each other and the robot arm went crazy and I had to use that kill switch that we put in one of the earlier chapters. So I decided that what I would do is make the system be in one of two modes, either the CapSense mode or the motion mode. FreeRTOS has the concept of event groups, which is essentially a thread-safe global variable. So we'll use one of these. The way this is going to work is that when the remote control is sitting still and flat for, I don't know, a while, let's call it 3 seconds, I'll put the system into CapSense mode. If you pick up the kit and move it around a little bit, it'll go into motion mode. To implement this, you need to include the event groups.h. Then make a definition for the event group called system input mode. This will actually be instantiated in the main CM4.c. Now I make a bit mask for the two modes. The double left arrow is the shift operator. Finally, let's define the motion task itself. Now I want to update the main CM4 to include the new stuff. First, include the motion task and the event groups. Next, I'll make the variable for the event group, which I'll call system input mode. Then in main, I'll initialize the event group, set the current mode to CapSense, and turn off LED 8. The last change in main is to start the motion task. Now, in CapSense task.c, I need to make two small changes. First, include motion task.h, and second, only call the right position function when you're in CapSense mode. Finally, the main event of this whole video, I need to create the motion task.c. I will copy from the basic motion sensors project's main_CM4. Specifically, I'll copy all of the includes all the way through the top of main, and then I'll paste it into motion task.c. At the top, I need to add includes for BLE task.h and motion task.h. Now, scroll all the way down to the motion task. I told you earlier that I will control the mode of the system based on the motion. If the board hasn't been moved in about a second, then I'll switch it into CapSense mode. So I need to declare a variable which I will use to keep track of the last time the board moved. Let's call that variable last movement. In order to calculate the desired motor position, I want to consider the X and the Y acceleration, meaning how the board is being held. In order to make the math easier, I will cap the acceleration at plus or minus 1 g. Next, I'll build a little routine that will convert minus 1 g to plus 1 g into 0% to 100% based on the angle the board is sitting at. Next, you should see the maths that I did to figure this out. The next bit of code is used to keep track of the last movement, meaning if the motor change is more than 3% from where it was previously, then update the last movement variable. Didn't feel like it was worth sending 1% increments over, so I didn't send anything for a 0% change, a 1% change, or a 2% change. Finally, if it has been more than 1 millisecond since the last movement, I'll set the system mode to CapSense and turn on LED 8. Otherwise, I'll set the mode to motion and turn off LED 8. If we're in motion mode, then we'll send the motion information. That's it. Let's test this thing. Let's see here. Hit the program button. And after a bit, you can see the remote control turns on, and then quicker than anything, it connects. See the red light turn on, and LED 8 turns on, indicating that the remote control is flat and not moving, and we're in CapSense mode. Now I'll slide my finger back and forth, and look, the robot arm moves. Now I'll pick up the remote control, and look, it turns off LED 8, indicating that it has moved to motion mode, and you can see the arm move in both axes. Now we have our fully implemented BLE remote control robot. In some of the later videos, I'll show you how to add Wi-Fi and cloud connectivity into the mix. As always, you can post your comments and questions in our PSOC 6 community, or you're welcome to email me at alan_hawes@cypress.com or tweet me at AskIoTExpert with your comments, your suggestions, your criticisms, and your questions. Thank you.